Welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Our today's speaker is Professor Agnès Beaudry from the University of Colorado Boulder, and she will speak about homotopy theory and phases of matter.
Thank you for the invitation to talk. So I want to discuss today some connections between algebraic topology, or stable homotopy theory, and condensed matter physics. So just a disclaimer: this is mostly going to be an expository talk. Though at the end I will mention some things that are closely related to, and some work that we've been doing with the collaboration that's going on at CU Boulder between the physics and the mathematics department, with also some people from other institutions. So my goal is to outline a program that we've been thinking about together with other people. There's a lot of people who are thinking about this problem right now. I won't try to be mathematically rigorous, so this won't be, I guess, like a typical math talk, but there might also be some questions about the physics that I present that I might not know how to answer, because I'm not myself a physicist, but I'm hoping that collaborators of mine in the audience will feel free to jump in and answer if there's something that I can't answer. Okay, so here's some information before I begin. So I've listed references here. There's lots of people, like I said, working on these kinds of questions, but so this is just a sample of places that you could go to start learning more after the talk. And the work that we've been doing, that is the motivation for that. Sorry, that's the the stuff that's going in the background. The research is funded by the following grants. Okay. All right. So I want to start by talking briefly about a classical example of phases of matter. So probably you've seen the phase diagram for water at some point in your life. We typically think of water as having three phases: the solid, liquid, and gas phase. And these are, they change depending on how we change the parameters, how we change pressure and temperature. So the gray lines in this diagram are the phase transition lines. And I want to bring your attention to this part of the diagram. So something happens when the pressure and the temperature are both high. I heard something, but I didn't. So something happens when the pressure and the temperature are very high. The liquid and the gas phase become indistinguishable. Okay, so you can pass between the liquid and the gas phase without going through a phase transition. So topologically, if we remove these phase transition line, this diagram parametrized by pressure and temperature has two path connected components. Okay, so in that sense, there really are two phases for water. There's the solid and the liquid gas phase. So going forward, I'll be talking about quantum mechanical examples. I won't talk about classical example like water, but I want you to keep that sort of topological feature in mind, because it's going to be a common feature of the other systems that I present. Okay, so let's start with an overview of the goal of the talk. So I don't expect, the point of the talk is to introduce at least intuitively what the things that are in these statements are. So the motivation for the problem comes from a conjecture of Kitaev. And the conjecture is that invertible gap phases of matter, so these are one kind of quantum phases of matter, are parametrized. And then these phases, if you let them be parametrized by a space X, so X here could be, in the previous example, I was making you think of pressure and temperature. Going forward, it'll be like a magnetic field or a coupling constant. And the conjecture is that such phases form a generalized cohomology theory. which I'm going to denote by GP star of X. So generalized cohomology theory is something called a functor, which takes a topological space and spits out an abelian group. Okay, so this is something that stable homotopy theorists are used to playing with and studying. Examples of generalized cohomology theory that you might be familiar with, if you don't know what this means, are singular cohomology, or cohomology, just the usual thing, or K theory. Okay, so now there's a accepted belief, among condensed matter physicists, is that these kinds of phases of matter should be captured by certain kinds of topological quantum field theories. So they should be fully described by these. Okay, and now if we take this as an axiom, then the work of Freed-Hopkins predicts what this group should be by computing what the certain kind of topological quantum field theory should be. So, and they using that that connection, the prediction is that this cohomology theory should be this one. So now I'm not going to explain what this cohomology theory is. The point is that this is something that is very familiar to stable homotopy theorists. We know how to compute these kinds of things. Okay, and in fact, this the values of the cohomology theory on a space X are completely determined by the oriented Bordism group of the space. So you have to do something fancy, but if you know how to compute oriented Bordism, then you can compute the phases parametrized by the space X. Okay. So, however, it's not like if there's a proof of this correspondence between field theories and invertible gap phases of matter. And so for the rest of the talk, I don't want to, the classical way to connect is with the kinds of things that I'm an expert in, is to go through, this, just talk about topological field theories. But what I want to do instead is talk about how one might come to such a conclusion directly from something called lattice models. So lattice models are idealizations of materials that physicists use to study phases of matter. Okay, so I'll come back briefly to this classification later, but that's not the point of view that I want to take here. Okay, so now I want to describe what these invertible phases of matter are. So I will sort of go briefly over an overview to describe what are the kinds of objects that we're trying to classify. Okay, so these phases, these are quantum phases. So to talk about them, we need some setup for studying quantum mechanics. There's lots of different axiomatic frameworks. So I won't get into anything complicated here. I'll try to convey the problem just using the most classical framework, which uses Hilbert spaces. Okay, but the warning is that when we're trying to do this rigorously, we actually pass to the C-star algebraic, framework for quantum mechanics. Okay. Okay. So what's going to be a quantum dynamical system? Well, first, we start with a complex Hilbert space, so that I'm going to denote by this script H, and unit vectors in that space I'm going to denote by psi. Okay. Now the observables are the self-adjoint operators acting on this Hilbert space, and of course, because they're self-adjoint, they have a real spectrum. Okay. So the pure states are the rays in this Hilbert space. So the projective, so the collection of these are from the projective Hilbert space. And to make a measurement is to compute the expectation value of an observable prepared in a certain state. And mathematically, this just means computing this inner product. Okay. And because a self-adjoint measurements are real. And I just want to point out that here I'm using the physical convention that this is linear in the second variable. Okay, so now the dynamics of the system are given by time evolution. So, and this is described by Hamiltonian H, which H is the observable that corresponds to the total energy of the system. And if you want to understand how a state evolves, in time, you can do that through Schrödinger's equation. The energy of the system is the eigenvalues of H. And quantum dynamical system, I just want you to think of a pair as a Hilbert space and a Hamiltonian. Okay. So now I said earlier that we were going to talk about that we were going to try to sort of understand the classifications in terms of something called lattice models. So lattice models, again, are idealizations of material, and they have a notion of spatial dimension. So we're not going to look at all the Hilbert spaces. We're going to think of those coming from these kinds of setups that I'm about to explain. Okay. So let me just go one dimension at a time, and then you can generalize in your head. So in 0 dimension, so what we want to think of is just a single particle, just a single particle in space. So that's why it's 0 dimensional. There's no the spatial dimension. We're not moving in any direction. Okay. And this is going to be modeled by the Hilbert space C to the n, where n, the dimension of the Hilbert space, is determined by the spin type of the particle. So then the observables, as in the previous slides, are just the self-adjoint n-body matrices. Okay, so in 1 dimension, what we're modeling is a chain of particles. So we're going to think of one particle on each of the lattice sites of Z, as we think of Z as sitting in R. Okay. So, and really, if we want to do this in terms of Hilbert space, perhaps what we're going to do is we're going to think of a finite chain, and we're going to take H to be the tensor product. So this H is modeling a particle on each of these sites. But really, we're going to think of n as going to infinity, and practically that means you have to ignore boundary phenomena. Okay, anything that comes from having cut the chain. And then the observables are going to be the self-adjoint operators in this tensor product. And let me point out that while this tensor product is harder to sort of define rigorously, this is fine. Okay. And then in two dimension or 3 dimension or higher, you do the same thing. You're just placing particle on a lattice. And the way you're thinking of this is you've got some n-dimensional material, and you've got particles, on that material, like the particles are forming that material. Okay. So now already in the previous slide, there was another dimension embedded in the way we thought about the Hilbert space, but the dynamics also capture the dimensionality of the system. And this is through something that's called locality, and the property that the Hamiltonian has to be finite range. So I'm going to describe what that means. So now we pick one of these, Hilbert space from the previous slide. We're thinking of n as going to infinity. And then we want the Hamiltonian to be a sum. So formally a sum, these terms H lambdas, they're going to be self-adjoints that are indexed by the finite subsets of the lattice. Okay. So H lambda is the thing acting on, the sites that are indexed by the elements in the subset lambda. And that the Hamiltonian has finite range means that there's some constant such that these terms are 0 whenever the diameter of the subset is bigger than the constant. Okay. So practically what that means is that particles that are very far apart don't interact. Okay. In your Hamiltonian, you might have single site terms that only sort of affect one particle. You might have coupling terms, maybe that affect nearby sites, so maybe neighbors, or it could be like, it could be something other than neighbors, but they have to be nearby. But there's a bound on how far particles can be to have an interaction. And okay, I'll say one last time, this kind of setup we can make rigorous with using C-star algebras, but I won't go there today. All right, so now let's look at some examples. That's what I want to do in the next slides, and use the examples to introduce other concepts that are important. So in 0 dimension, so the first example would be a spin-a-half particle. So for example, an electron. So we're in 0 dimension, so we just have a single particle. The spin-a-half particle has 2 modes, up and down. So then the Hilbert space that we use is going to be C2 on these two modes. Okay. Now the observables then are the self-adjoint 2x2 complex matrices, which are the R spans of the identity matrix together with the Pauli matrices. And these Pauli matrices represents magnetic fields in the XYZ direction. So you think of your electron as sitting in space, and then you've got you can influence it with magnetic fields in the 3 spatial dimensions. The pure states are just the rays in C2, which is a well-known space, which is CP1. And an example of a possible Hamiltonian is just going to be the sum of the Z Pauli matrix with the identity. And if we take this Hamiltonian, then the energy, so the eigenvalues are 2 and 0 with corresponding eigenvectors. And 0 here is important. That's the lowest energy. And the corresponding eigenspace is called the ground state. So now in this example, as with often is the case in 0-dimensional example, we have the lowest eigenvalue, and then there's a positive gap between the next one. And in this case, the lowest dimensional eigenspace is 1 dimension. Okay. So unless all the eigenvalues are the same, you're always going to have a gap there because it's a finite set of the spectrum. But here the important part is that the lowest energy is 1 dimensional, and in this case we're going to say that H is uniquely gapped. Okay. So more generally, suppose that I'm going to say that H is uniquely gapped if the spectrum of H looks like this. All right. So bounded below with I'm going to call E0 the lowest energy. There's a gap between the lowest energy and the rest of the spectrum. And the ground state is 1 dimensional. Okay. And in this, right. So I just want to point out that, this E0, we might as well assume that it's actually equal to 0. Okay. Because you can always just shift the Hamiltonian to make that true. So now, why are these important? So suppose that the temperature is small with respect to the energy gap. Well, then the system will default to its ground state. So at very low temperature, the system is stable, and things like current won't flow. Okay, so these are the kinds of systems that we want to classify, or that Kitaev's prediction is talking about. All right, so let's look at another example. So earlier in the water example, there was a parameter space, right? There was pressure and temperature, and you could tune these. Okay, so and these are the kind of systems that I'm moving towards talking about. So here's a simple example of such a system in 0 dimension. So again, you have a spin-a-half particle, but then you imagine that you've got the Hamiltonian is a magnetic field, but you've got some knobs, and you can tune it, and you can vary the direction in which the magnetic field is acting. Okay. So for each point XYZ in the 2-sphere, so the 2-sphere parametrizes the direction in R3, the directions in R3, you have this energy. Okay. So you can compute that at any point on the sphere, the spectrum is always -1 and +1. And then you can also compute that the ground state is the linear span of this vector Cx given by this formula. So in particular, this is at any point in S2, this H here is uniquely gapped. Okay. And now I want to point out then we see topology emerging. Over here, so we have this, for each point, we have a line, a complex line, and these actually assemble into a line bundle over the two sphere. Okay. And this line bundle is not trivial because this section here is not continuous. Okay. So we get a non-trivial line bundle formed by the ground states of the system. So we'll come back to this later. All right, so now let's look at a 1D parametrized example. So this is the Ising model. So now we're in one dimension, and we're just going to think of a spin-a-half particle on each lattice site. Okay, so the Hilbert space is going to be the following, but we're thinking of again as n going to infinity. So you have to ignore boundary phenomena for the statements that I'm going to make to be true. So the observables are the self-adjoint in this matrix algebra. So for example, if I have a Pauli matrix, I can put it just on a single site, and I'll denote this by sigma z sub j. Okay. And the Hamiltonian for the Ising model is the following. It depends on two parameters. There's a constant h which is the magnetic field, and a constant j, which is a coupling constant between neighboring sites. Okay. And the ground states of the system, that depends on the parameters h and j. Okay, so as you vary h and j, you're going to see different phenomena happening. So over here, I've just repeated the Hamiltonian from the previous slide. And over here, we have the phase diagram. So we've got two parameters, the magnetic field and the coupling constant. And depending on how they relate to one another, the system may not be uniquely gapped. It's uniquely gapped only in these two regions over here. Okay. And now if we take out from this, from this two plane, if we take out any points where the system is not uniquely gapped, we actually get two components because we're taking out this and then all of this. Okay. So there are really two different phases in which Hamiltonian is uniquely gapped. And again, as long as I'm on the side, this is a path component, right? So I can continuously deform the Hamiltonian by varying h and j continuously to get from any systems on this side to any two systems that lie on this side, and similarly for that side. Okay, so anything here is in the same phase, and same for this. All right. So now I want to introduce two more notions, the notion of triviality and stacking. Okay, so what's a trivial system? So if your Hamiltonian is a sum of single site terms, okay, so here there are no couplings. So for example, the Hamiltonian could just be, a sum of a Pauli matrix on each side. Okay, then we're going to say that such a system is trivial, and here hj here is just, you just, like I did before with the sigma zj, you just put h on the j site. Okay. All right, so why is this trivial? Well, so we're trying to sort of classify interactions, between particles, and in such a system, there's no quantum interactions between the sites. Each particle can exhibit quantum behavior, but the two neighboring particles don't interact in that way. Okay, in other words, these terms here, they commute. So we're going to think of this as a trivial system. And then the next notion is that of stacking. So now suppose you have two systems, think of them as, like, say in 2D, two sheets of material. Stacking is just put them on top of one another, okay? And don't make the different sheets interact, okay? Mathematically, you just take the tensor product of the Hilbert spaces, and then you take these two terms. And again, these terms commute with one another, so the two sheets are not interacting. So this gives a binary operation on the quantum systems. Okay, take two systems, you can stack them. So now we're going to make the jump. Okay, so at this point, I've described to you how you should think of, like, how I'm going to think about quantum systems in spatial dimension d. So that's the size of the lattice. Okay, and the key to jump into the topological land and the stable homotopy theory is to imagine that you have a topological space of such data. Okay, so the points of the space are uniquely gapped Hamiltonians in dimension D. Okay, so now the warning. There are no rigorous definitions of this physically or mathematically, though there are like currently a lot of work and ideas going around to actually sort of make this realizable. And, you know, I don't think this is out of reach of like really sort of nailing down what one might mean by that. Okay. Another warning is I describe certain systems, so certain how I imagine of the points of the space to be, but you might need further restrictions on the data. So for example, you might want to restrict a system that are related in some way to those that have translation symmetry or other things. Okay. But so the key to understand Kitaev's prediction in the terms of a generalized cohomology theory is to proceed formally and assuming that there exists such a space. Okay, so quickly you might imagine, if you're taking the C-star algebraic approach, you might imagine looking at interactions, finite range bounded interactions, and tweaking the topology so that you know, when you go through a path, you never close the gap if there's one. Okay, so you can sort of tweak the topology on that thing. The usual one won't be the right one, but there's ideas on how to go about that. But I won't get more into that today. Okay, so for now, let's go on a journey and let's assume we have a space, okay, and see what we get out of it. So now, if X is a finite CW complex, so if you so if that makes you unhappy, just think of a really nice compact space. Okay, so a manifold. That's not equivalent, but I just you can think of a manifold and you won't miss anything. Now a parametrized system is going to be just so for each, so a parametrized system, we think of X as the parameter space, so maybe it's a magnetic field or the coupling constants, and we want to have for each value of the parameters, we want to have a system. So mathematically, that's just a continuous map from the parameters to this imagined space of d-dimensional gap system. So like before, we had our two sphere, and on each point of the sphere, we had a Hamiltonian in 0 dimension. And you imagine the same thing, except that now on each point, you could have like a d-dimensional quantum system. Okay, so in terms of parametrized system, the trivial system is going to be the following. So a system over X is going to be trivial if the function that you get is constant. Okay, and the constant value is a trivial system in the sense of the previous slide. It's completely decoupled. There's no interactions between the sites. So for example, a trivial system, you could take S2 and then you could put this Hamiltonian. Here I've opted to use the different notations for the Pauli matrices because I want to make it clear that this here, the point is it doesn't depend on X, Y, Z, the points of the two sphere. And just like I could stack system, I can stack systems that are parametrized. You just stack the values. So you evaluate and you stack in the evaluation, and that gives you a new map. Okay. So then with this sort of notion in mind, we're ready to talk about what phases are. So a phase then is going to be an equivalence class of system. For an equivalence class relation generated by the following things. Okay, so basically we want to sort of enumerate or understand when should two systems be in the state phase? What should that mean? So the first notion is a notion of isomorphism. So if I have two systems and I've presented it in a certain way, maybe I've done something like choose a basis for the Hilbert space the Hilbert space on one of my sites. But that choice of basis should not be relevant. So if I change that choice or I change the way that I think about the system in that way, I should not change the system. I don't want to think of these two systems as being in different phases. In fact, I don't even want to think of them as being different. Okay. So this is the notion of isomorphism. So you can change sort of your frame on each site without changing the system. Okay, so the next definition is more related to the examples with the easing model or the diagram for phases of water, like that intuition that I was trying to build. So suppose that you have two systems, and what does it mean to be able to deform a system into another continuously? Well, topologically, that means that the two maps, H and H prime, remember they're maps from X to this space of the dimensional system. This means that they're homotopic. So in other words, there's a map from X times an interval, I, so I is the interval 0, 1, okay? And so at time 0, you're just doing the map H over here, and at time 1, you're doing the map H prime. Okay. All right, so now, the next notion of when two systems should be equivalent is the following. So suppose now I have two systems, and suppose that I have trivial systems. So remember, trivial systems are those that there's no couplings, so there's no quantum interactions between the sites. Now, if I take H and I stack it with a trivial system, that stack also doesn't put any interactions between the two sheets. So I have, like, if you stack with a trivial system, you haven't introduced any new interactions between sites. So that shouldn't change the phase of the system. So the equivalence that witnesses that is that if you stack with trivial system, if you can sort of identify two systems after stacking with trivial system, that these should be in the same phase. And then I've put the bulk boundary correspondence here. I won't talk about it, what it is. There might be, so let me just put it this way. So these are three things that definitely need to be part of your notion of what it means to be in the same phase. The hope is that this is sufficient, that really this is it. But at this point, this is a mathematical modeling problem. So there are certain systems that condensed matter physicists think of, and we're trying to model it. So this is like maybe a first attempt at doing it. I don't think there's a proof yet that this is sufficient. Okay, that this is really captures everything.
A quick question. In practice, is X often just a point? Is that interesting enough if X is a point? Because if I look at these definitions, it seems to be a reasonable definition of a phase of matter if X is just a point.
Yeah, so if X is a point, it's supposed to capture what you think of just a phase of matter that's not parametrized. Exactly. The point, like classical, like what you might read about, like, oh, the phases before is over a point when you put X to be a point. But the parameter space, so the key here is that the parameter space X could capture more subtle topological properties of this this space here. So for example, so here I had it on a slide. I said like bosonic with no symmetry. So I've been secretly, that's what I've been having in mind. You can change that. You can look at fermionic, or you can put some symmetries in the system and sort of tell a similar story. But in the sort of most basic case, say in dimension 1 or 0, it's understood that the phases over a point are trivial. There are no non-trivial phases over, in one dimension for bosonic system with no symmetry. However, that doesn't mean that there are no non-trivial phases parametrized by a more fancy space X. So already in dimension 0, I'll come to that. The example of a spin-a-half particle in a magnetic field over S2, that's a 0-dimensional system parametrized by X, and it isn't trivial over S2 because of that line bundle. So I'll come back to that later. So it sort of tells you something that you might not just see over a point. Does that answer your question?
I actually misread your definition a little bit. Okay. Thank you.
Okay. All right. So okay, so here I've just repeated these equivalences, and now we're ready for the definition. So of this cohomology theory, well, not quite. This is like step 1. So now now that we have this equivalence class, we could look at continuous map from X to the space of d-dimensional gap Hamiltonians, and we could mod out by this equivalence relation, and then the resulting thing that you would get would be this notion of an element here would be a phase. So in other words, it's an equivalence class of system with respect to these things. Okay. Now it's something that you can show, you can proceed formally and show that whatever you're doing, I mean, this thing that you get is better be a commutative monoid with respect to stacking. Okay, so stacking respects phases. And the unit for this monoid will be the trivial phase. This comes from the fact that we've imposed that stacking with trivial systems did not, was a phase invariant. And then whenever you have a set which has a distinguished point and a base space, then you can talk about the kernel of the map induced by the inclusion of x naught into x. So now I just want to show, so if I put x naught into x, now if I apply this assignment here, well, continuous function, if I have a continuous function from x to these systems, then I can precompose with the inclusion of the base point, and then I get a function from the base point to the system. So now these are phases over a point. Okay, so just phases. And then the reduced phases over x are just the kernel of this map. So these are, so in other words, so you're going to have a system parametrized by the space x, and all you're asking is that over the base point, that system is trivial. Okay. And now if you look at this reduced functor, then you can show that this is a Brown functor. However, it's probable that just in the generality that I define quantum system, you're not going to get the countability axiom for the Brown functors. You probably have to sort of restrict even more. Otherwise, you're probably going to get too much stuff. Okay. Let's see. So I want to go back to this example. So let's look at 0 dimension. So while the space GHD for general D, I asked you to imagine it. In dimension 0, you don't have to imagine it. It's pretty simple to understand that this space here should be the subspace of the disjoint union of n by n matrices, where you're restricted to self-adjoint matrices with one-dimensional lowest eigenspace. And that's because you want uniquely gap Hamiltonians. So a 0-dimensional system over X is going to be a continuous map from X to these spaces of matrices. So in other words, for each point in your space X, you're going to have a self-adjoint matrix. Okay, and it's going to vary continuously with respect to the parameters X. So now, because of this condition, at each point of X, we can form the ground state for the Hamiltonian. So that's a complex line for each point of X. And these assemble into a line bundle. So you can make this rigorous. This whole picture at dimension 0, you can make completely rigorous. And the thing that you can prove is that with the relations that I gave before on the previous slide, that the only phase invariant, like when you take into account all these equivalence classes, the only invariant that remains is the isomorphism class of this line bundle of ground states. So that means that 0-dimensional phases over X are are isomorphic to the second cohomology group of X, because line bundles are classified by this group via the first term class of the line bundle. Okay. And again, we had an example of our spin a half in a magnetic field. That's an example of a non-trivial 0-dimensional phase. So this generates H2 of S2, which is a copy of C. Okay. So going back, if I stick X as a point, I will get 0, right? The second cohomology of a point is 0. But if I look at a more interesting parameter space, I will get non-trivial things. So now invertible phases is the last ingredient that I need to put in before I can go back to Kitaev's prediction. So there are some phases that are special. So a phase is going to be called invertible if there exists another phase such that if you stack H with that other phrase, so aka the inverse, you get something that's in the same phase as the trivial system. So get something in the trivial phase. So now you can restrict. We had all gap phases. You can restrict and just look at those gap phases that are invertible. And now without the invertibility, we had a commutative monoid. So if you restrict to the invertible thing, you get an abelian group. Like all you were missing were inverses, and you've restricted to those elements that do have inverses. Okay, and now Kitaev's prediction is that this assignment, X goes to the invertible phases over X, forms a generalized cohomology theory. Okay. So the key to showing that this is a generalized cohomology theory, the only thing that doesn't, that seems like it's not going to be formal, is the suspension isomorphism of the theory, and I will come back to that in 2 slides. Okay. And things that you can show almost formally, though not quite, that we've been able to think through in our collaboration, is that something kind of special happened if you look over the suspension of a space X and it turns out to be invertible. So in other words, if you have a gap d-dimensional phase, an example, not in other words. For example, if you have a gap d-dimensional phase over the circle S1, no symmetry here, then that phase has to be invertible. Okay. All right. So now I just want to revisit the Freed-Hopkins prediction. So again, if we believe that invertible phases are completely described by certain kinds of topological quantum field theories, then the answer should be this, okay, whatever that means. But now I've put some values. So in 0 dimension, you expect line bundles, like I explained earlier. In 1 dimension, you expect that there's only one invariant, which is captured by the 3rd integer cohomology group of X. In 2 dimension, then you get something new. You get something that's beyond cohomology. So there's a new phase. The generator of the Z is Kitaev's EH phase. Okay, so suddenly you see some new things, and this is a manifestation that bosonic phases with no symmetry are, that there's a non-trivial one. And in general, you expect some piece, and I was careful here to just put approx, okay, an approximation. So you expect some piece of phases that will be captured by just regular singular cohomology, and then some other part that goes beyond cohomology, like Kitaev's phase. And in recent work, I think it's 2020, Kapustin and Spodinenko actually wrote down a D+2 form in the Durand cohomology of a manifold that you might call the higher Berry curvature, or we like to call the KS invariant, that detects this piece over here. Okay, so if you have a D-dimensional system over a manifold, you can sit down and hope to compute that form and check if it's non-trivial or trivial. Okay, so now I want to come back to Kitaev's suspension isomorphism. Okay, in general, if you have a cohomology theory, a generalized cohomology theory, it comes, so one of the axioms is that there is a suspension isomorphism, and this says that the reduced phases over a space X, or the values in dimension D of the cohomology theory, are related to the values of the cohomology theory 1 dimension above, but now parametrized by the suspension of the space. Okay, so I'm gonna, if X is nicely base, this sigma X is the same as the unreduced suspension. So if you don't know what that means, I'm going to explain it. Okay, so the suspension of X is this following picture. So if you have a manifold or space X, then you form the suspension by gluing 2 X-shaped cones over X. So you have a time parameter But when you get to t is equal to 1, so this picture is a quotient of x cross 0, I guess minus 1, 1. Okay, and at the top of this x-shaped cylinder, so this is like x, you crush the top and you crush the bottom to 2 points. So that's a sort of classical construction in homotopy theory. Okay, so that's the description of the parameter space for this side of the isomorphism. And now the point is that Kitaev gave a sketch of how if you take a d-dimensional system, then you can get a d+1 dimensional system over the suspension of x. To be strictly speaking, this is not how Kitaev phrased it. Kitaev discussed how you can form a loop spectrum, but loop spectrum and generalized cohomology theory are intimately related. And we're taking the perspective of trying to sort of study the generalized cohomology theory rather than the loop spectrum itself. Okay, so here's what you do. Roughly, you have a system H. So this is a d-dimensional system. So I've sort of depicted that by putting H on a sheet here that I've labeled Z. Okay. Now you imagine stacking alternating copies of H and its inverse. Remember, the system is invertible, so it has an inverse. You just create this infinite stack, and it gives you a new parameter, which is, you have a system on a parametrized by a d+1 lattice. Okay, so this is this is a d+1 system that you can form from a d-dimensional system. Just alternate stacks of H and H inverse. And this is what you're going to put at time 0 on the suspension. So remember, for each point in this picture, we wanted a d+1 dimensional system. So you put this alternating stack here. But now, if I just focus on these two sheets, neighboring sheets, I mean, this is the stack of H with its inverse. Okay, and that's in the trivial phase. So up to maybe making some small modifications, you can write a path. You can deform it to be in the trivial phase. So there's a path from H inverse and its stack that deforms to the trivial phase. Okay, and what you do is in that time coordinate going from 0 to 1, you use that path to define the system at each time. Okay, and at the end here at time t, at the top, the system remember, a trivial system doesn't depend on x, it's constant. So it's all the same system at time 1. So that's why it makes sense to define it on this coin point. To just it's the same on all of x, so you can sort of just say, okay, that's the value at this coin point. And then, okay, on the bottom half, you do something similar, but instead of pairing the inverse of H with H, you pair H with its inverse. Okay, and then you deform. You pick. There's a path. It could be a different path, and you deform it to some trivial system over there, and then that's the value at that point. Okay, so then you get a d+1 system. Okay, so the conjecture, sorry, is that this construction on phases gives an isomorphism. Now, if you look at what I'm saying, there's a lot of choices involved, like the system, which system represent do you pick? What's the inverse? What's the path? Which trivial system, all of that. There's lots of choices, but these are choices in the systems. And the conjecture is that if you just look at the induced phases, then this is well defined and it gives you a function, a bijective function. Okay. So I want to discuss the suspension as an example of the 0-dimensional example of a spin, a half, and a magnetic field. So this is from a previous slide. Okay, so this is going to be, so the system we start with is a system over S2 in dimension 0, 0. And now we will want to get a system over the suspension of S2. And we want that to be a 1-dimensional system. Okay, so I'll do that in the next slide. So the suspension of the 2-sphere is homeomorphic to the 3-sphere. So what I'll describe is just a system on S3. Okay. So let's parametrize the 3-sphere as quadruples of real numbers whose square sum to 1. Okay. And now this is, again, we're trying to suspend this system over S2. if T is 0 here, I just get a copy of S2 embedded in S3. Okay, that copy here is the equator of the S3 sphere. So I drew S3 as S2 because I can't draw S3, but just shift your dimensions up in your head a little bit. Okay. All right, so on that equator of S2, so now we need to define a Hamiltonian that's supposed to model this suspension isomorphism. So here's one way that you can do it. So there's going to be 3 terms in the Hamiltonian. So one term, the first term is just single side terms. So on side J, you put this system. And for J is even, this is just the same as that. When J is odd, it's the inverse. Okay. So here, this is just that stack of, I had on the previous slide, I had H inverse, H inverse. This is this term over here. Okay. And that's sitting there at the equator. Now X, Y, Z here, there's no so this system here, there's not strictly a T dependence, but as T goes to 1, X, Y, and Z go to 0. Okay, and similarly, as T goes to -1, X, Y, and Z go to 0. Okay, so at the north and south pole, you actually just get 0 here, and then you have a problem. You'd have a gap. Okay, but that's okay because we'll compensate with these coupling terms. So what do we do? So there's 2 kinds of coupling terms. Some of them are for the northern hemisphere, and some of them are for the southern hemisphere. And these corresponds to these paths between H and the stack of H and its inverse to the trivial system. Okay, so I won't describe them, but you can write them explicitly. And then you get a system over S3. Okay. So now one of the things that we have shown, and this will be in a very soon to appear paper on the archive, is that if you do this and you compute the KS invariant, then you get a generator for H3S, 3Z. Okay. So it's easy to check that the 0-dimensional system generates H2 of S2. And H2 of S2 is isomorphic to H3 of S3 by this, classical suspension isomorphism. And you can compute that this construction here ends up giving you an isomorphism between the H2 and the H3, which are the expected classifications in these dimensions for these spheres. Okay, so this is evidence that Kitaev's conjecture might work. And you can iterate this construction, and in fact, you can generalize it to something that's to any 0-dimensional system. So you can generalize this procedure. And in our paper, we study the higher KS invariance for such constructions, and say things about them. And then, okay, so maybe the last comment I want to make, and I'm not going to get into it, is that so what's a physical interpretation of the suspension? So if you have a system over X, there's a construction very similar to the suspension isomorphism that I gave there that produces a system over X cross S1. So X cross S1 is an X-shaped torus. Okay. And this S1 is the S1 here represents a periodic parameter, and this suspension construction, or the corresponding construction here, is supposed to model a pump. Okay, so it's supposed to be a generalization of the Pflaum pump. So so that's to sneak preview of like where maybe this might come from. And that's actually the last thing that I wanted to say. I'm hoping that, I know there's lots of things that were unsaid, lots of things that are left, that are not rigorous, but this is a general program that people have been thinking about to sort of try to study phases of matter. And I hope that it gave you some kind of general idea of what's going on in the background. So thank you for your time. Again, these are references to get you started if you want to know more about all these things.
Yeah. Thank you very much, Agnès, for the nice talk. Are there questions? So. No questions so
On
far.
the matter of
Yeah.
points, again, should I usually think of the space X as being at least equipped with a base point, or that is also not necessarily?
It's a choice. You don't have to. So you can have phases over a non-base space. If you want to relate the d-dimensional phases over X with the d+1 phases over the suspension, which is really this is like the non-trivial content of the statement, is that there should be that relationship. So then mathematically, you need like you need to pick a base point, and then you need to focus on the reduced phases. So in other words, like the way you want to think about the reduced phases is that you've got like a phase over X, just think of a tooth sphere. And at each point, you're actually in the trivial phase in that dimension. Okay, so at each point, you might have a system, might not be trivial, but it's in the trivial phase, because at the base point of X, you've asked that system be trivial. Okay, so you've got like, so maybe like locally, everything looks trivial, but the point is that these trivial phases have been like braided together, like in an X way, like to be non-trivial. So you couldn't bring everything back to a trivial system without breaking continuity or without ignoring the topology of X. So that's how you want to think of the reduced phases. Yeah. But no, you don't have to think of X as having a base point. Yeah.
Okay, thanks.
Further questions?
So Marcus, can I ask a question?
Yeah, sure. Hi, Sean. Please.
Hi, Marcus. Also, hi, Agnès. Nice
Hi,
talk.
how are you?
Yeah.
Nice to see you.
Yeah, nice seeing you. So can I ask a question? So
Yeah.
about this generalized cohomology, you had H1, H2, H3. So and then there's a whole hierarchy, the towers, right? So
yeah, let me go to that slide. This one. Go ahead. Oh, sorry.
Sorry. So about
No,
this
okay.
one, so do you have any kind of conjecture or guess about, say, for the higher structures, what kind of a geometric or topological structure do they correspond to? Like H4 and even HD+2, what are they?
Oh, so okay. Well, the general conjecture is that the values are actually equal to this thing. Okay, so there's a torsion part which comes from the Bordism classes of oriented Bordism classes in dimension d+1, and then there's a free part that comes from the oriented Bordism classes in dimension d+2, and these H4 Z here, they correspond to these cohomology bits. They're coming from this free bit. Okay, and now I'm forgetting the word, but so these are supposed to be generalization of what's the name? So the things they construct in Descartes-Witten. So what's the name of that? Daniel and Juan or Marcus? I'm forgetting.
Are you talking about the West-Zumino-Witten term?
Yeah, those kinds of terms, and there's a concrete example of it that I'm forgetting the name.
Okay, maybe I'll ask you later.
Well,
after the talk.
Yeah, I'm just totally blanking these corresponds to generalization of these field or these action maps that people like to think about. But I'm forgetting the name of the most. It's detected by the Pontryagin class. Juan, can you help me? You don't remember the name. The thing where you take you take the integral of the trace of the first Pontryagin class or something. Anyways, I'm forgetting.
Are you looking for Chern-Simons?
Yeah, thank you. It's like generalization of these Chern-Simon terms.
Yeah. Okay.
Yeah. Thanks, Marcus.
Okay,
Yeah.
thank you.
So this is this bit is supposed to be that. Yeah.
Okay.
If I'm not mistaken. Yeah.
Actually, Shang, I mean, do you want to continue or because I have a question which is related to this somehow, but please.
Okay, then yeah, but well, I have a question in another direction. Probably you can ask Marcus. Yeah, that's probably better.
Yeah. Yeah, so it's kind of a little bit connected, but I mean, there's this whole theory of non-abelian cohomology, and the line bundles, well, are, I mean, related to the non-abelian cohomology in degree 1. And what's your impression? Do you think there is some relation with this? I mean, which goes back, this theory goes back to Giraud and others. And actually, John Roberts, a famous mathematical physicist, has worked on this. And it seems there are some recent new results by Ross Street. And somehow, I don't know. I mean, it's there are some similarities, but do you have?
Yeah, unfortunately, I'm not really familiar with non-abelian cohomology, so I can't give a sense.
Mm-hmm.
What do you think, Marcus?
Yeah. Well, actually, yeah.
This is, I don't have. I'm not. I mean, you're part of the collaboration. So.
Yes, no, that's true. It is. I mean, I'm asking this question because I mean it's more a gut feeling that there is a relation, but I don't see it yet.
Yeah.
And I mean, yeah. That's what I can say on this.
I mean, there's lots of work on differential cohomology and sort of geometric models and there's a new paper coming soon that sort of describes the sort of a geometric model for this over here, and sort of relates this kind of problem to field theories, relates this cohomology theory more closely to field theories from perhaps done before, but I'm not sure. Yeah.
Sure. More questions? So, yeah, Shang.
Can I ask one more question? Sorry.
Yeah. Yeah. Please go ahead. Yeah.
Yeah. So in your kind of mathematical models about this, whole system. So
yeah.
Did you kind of include the information or kind of distinction between the kind of a short range interaction and the long range interactions? Maybe you did it, but just
I think so. So as far as my understanding goes, my talk was about the short range entanglement. So maybe I'll leave it at that. That's maybe if somebody in the audience has more to say on that, then they're welcome to speak up. I'm happy to have this be more discussion. But yeah, this is all like short range entanglement stuff.
So any thoughts or any kind of conjecture about the long range or kind of?
I'm sure there are, but not necessarily from me. Yeah. So there's a talk on YouTube by Kapustin from like 2 weeks ago that I think discusses this kind of stuff. So maybe you could go see there. But yeah, I'm not sure. Like I said, I really am, like we're quite a team, an interdisciplinary team, and you're gonna hit my bottom in terms of what I can answer from the physics perspective quicker than I would like. So yeah, but I mean, I see Shweda's in the audience. He's welcome to speak up if he wants to. He might be able to answer.
Thank you. Yeah, thank you. I really appreciate the answers. Yeah, thanks.
Yeah, I have a question.
Yeah, and I apologize if I said anything that was wrong. I'm doing my best to sort of convey. This was a talk prepared for topologists, so so maybe that shows. Yeah.
No worries.
No.
I have a question. Is there like a multiplicative structure on this cohomology theory? And can you get that from something physical?
So this thing is sigma 2 of IZ-MSO, and IZ-MSO is a ring. So while sigma 2 IZ is not, So there is sort of a ring in the background. So if you sort of desuspend, so if you sort of change your, like if you desuspend, then you'll get some pairings. And that's a really interesting question, what those pairings mean. I've not thought about it, but I've been, wanting to get someone to think about that. That's interesting. Yeah.
Thanks.
So yeah, there should be pairings lying in the background. They might not come to you just in exactly the way that you expect them from a generalized cohomology theory, but up to suspension, you should see something. But
okay, I think Marcus is about to head out. So are there any other questions?
Before we I wanted to say the thing I said earlier about sort of understanding this in terms of field theories and a geometric model. That's a recent work by Mayuko Yamashita from Kyoto. And I just wanted to mention her name because I mentioned her results. So before we stop the talk.
Okay.
You can stop it. Yeah.
Okay, well, let's thank Agnès again, and I'll stop the recording.